Our speaker today is Andre Souza, who's a research scientist at MIT. He's in the Department of Earth, Atmospheric, and Planetary Sciences. He works with Dr. Ferrari, and his research interests span a lot of topics. I'll just name a few: optimal control methods for bounding transports, quantities of interest, rare events and dynamical systems, machine learning methods for discovering dynamics, and more. And currently, I believe he's working on novel parameterizations for the ocean component of the climate model. And Andre, I actually saw your talk at the last AGU. I believe like you were talking right after or before Pierre, so I just happened to see your talk by chance. I thought it was super interesting, so looking forward to your talk today. Thanks.
Awesome. Yeah. So what I'll do today is go a little bit more in depth on one of the topics I lightly touch on at AGU, because there you have 8 minutes to encompass years worth of effort, right? So very much condensation of what's possible to say. I'll go ahead and start sharing my screen here. Okay, so everything should be shared. Okay, everyone see the presentation? All right, so today I'll be presenting a bit of the work I've been doing here at MIT with friends and, well, friends that are not at MIT as well. So work with Simone, Catherine, Toby, Raf, and Glenn as well. And this is all grown as a part of this MIT Climate Grand Challenge project, where we're essentially trying to create emulators of climate models. And this was a part of the exploration of using generative AI methods to create emulators for systems. We do have a preprint on everything that I'm going to be presenting on today, but if you look up surface to seafloor Andre Souza on Google, you'll probably find the preprint as well. So I'll go ahead and just jump straight into it, but I just want to preface everything by saying that at any point, if anyone has any questions, please feel free to stop me, interrupt me, and just ask a question on a given slide. I'm perfectly happy to address things on the spot. Okay. So before jumping directly into the methodology, exactly the connection between AI and climate, I just want to start with a kind of a philosophical point, which is comparing traditional machine learning methods to generative methods, and just how we perform scientific inquiry in general. So oftentimes we seek some kind of functional relationship between some kind of information that we have and some kind of information that we want. In the case today, I'm going to be talking about having measurements of the ocean surface and saying something about the currents on the ocean underneath, for example, velocity fields or temperature fields, some depth below the surface. And typically we identify these relationships with a mapping, something that directly from one input gives just one output, as is the definition of a function. But with generative models, instead, you no longer ask the question of doing a single unique output. For the information that you have here represented by X, you instead represent a probability distribution of possible outcomes. So not only just getting one answer, but a range of answers, some being more plausible than others, as captured by the density. So this is more akin to probabilistic inference or statistical inference. And they are related to one another. For example, the y equals f of x case is just a subset of what's possible to be represented with a row of y given x case, because, well, if you have a deterministic relationship between this quantity x and y, then this is just represented as a probability density as a delta function as a relationship between y minus f of x. So this is how generative methods generalize what we typically do when just trying to do an inference task. So a small example of this is if you have the function y equals x squared, and if you ask, okay, what's y given x? Then, well, you just, let's say you have -1, you square it, you get 1. Or in terms of probability densities, the probability that you get 1 when you plug in -1 into the function is, well, in density, infinity, but probability 1 in a small range of that answer. Of course, when you go backwards, though, and you try to ask, okay, what is X given that I know Y? And this is where you start seeing the flexibility of these probabilistic formulations or generative models, because for a given X, there isn't a unique Y, right? We could have plugged in -1 into the formula and gotten Y equals 1, or we could have plugged in 1 and also gotten 1. So there's kind of two answers that you could have get if you try to go backwards. Now, typically in physics, we have some method of doing branch selection, saying like, okay, this is actually the answer that we want amongst all possible choices. But with a probabilistic formulation, you don't need to necessarily make a branch selection or add in extra information beyond the question that you asked. So in this case, the probability density would be, let's say, a weighted average between two different delta functions. It's a 50-50 shot that you get the positive branch or negative branch. So if I ask what's X given Y, there's a 50% chance of +1 or a 50% chance of -1. And this is how we can go beyond just asking well-posed questions using probabilistic inference. And one other nice part about probabilistic inference is that if we know that we're conditioning on something that's extremely informative, we know that we're going to reduce back to the deterministic case. And the absolute worst case scenario for this probabilistic inference is just that we reduce to the marginal of Y, meaning that instead of getting a unique answer, we just get all the possible ranges of anything that we've ever seen before. It just means that the value that we plugged in isn't informative for reducing the range of possibilities of Y. So stated differently, a very well-posed question is to do things in this statistical formulation where you're trying to do a probabilistic inference as opposed to the regular inference method. But there is a connection between the two, at least if you're minimizing an L2 loss, where the f of x that you get out from the ill-posed formulation, at least in a traditional L2 loss for deterministic machine learning, can just be related to the expected value over y of this conditional distribution. So, for example, in the case of this branch selection of either being +1 or -1, it would average the two and always produce 0, no matter what value of x. And that already kind of gives you some hints as to what could be going on when people try deterministic machine learning approaches in cases where the information, the functional relationship that you're trying to specify isn't unique. This can go to have applications in, let's say, weather modeling, where if you try to predict over too long of a time scale, you wash away too much fine scale information. That's because the large scale features are maybe extremely predictable over a long time scale, but the very fine scale features get washed away in this expected value. If you provide a generative model, you're no longer going to have a unique answer, but at least you have an answer that has all the high resolution features that you cared about. So that's, let's say, the weather context for something like this, and why typically these generative models give you fields that are better looking than just deterministic methods. It's expected values wash away detail. But what we can do now that we really couldn't do before, at least in the past, is that what we condition on and what we try to infer can be extremely high dimensional. And I don't mean high dimensional like 3, 4, 5 dimensions. I mean, if you have an image and it's made up of 128 by 128 pixels, then this would be a 10,000 dimensional object. Each pixel has its own probability distribution. And you also care about all the correlations, triple correlations, quadruple correlations between all the pixels with every other pixel. So this is the kind of thing that we can do now with generative methods and neural networks that we couldn't do before. Of course, we need data, but assuming we have data, then we can learn these statistical regression models. So everything that I'll be discussing today uses score-based diffusion models. I'm not going to talk about the methodology so much. It was established in 2019. Arguably, the methodology can even go back to the 1920s in statistical mechanics. But what makes modern times different is that we can actually parameterize these distributions in a very nice way. And here I'm going to be using a modified unit architecture for all the training and everything else that I do. And as I mentioned before, it's all going to be information that we have is the thing that we're going to condition on. And then we're going to want to infer something that we couldn't infer otherwise. And so for today, I'm going to be talking about conditioning on the ocean surface and trying to predict the ocean interior. And there's many reasons why we'd want to do this kind of inference. One has to do with the global climatology of Earth, whether you care about the heat transport of the ocean, carbon uptake, or just other features of the ocean interior that you'd like to make some inference on. And using the information that we have plenty of, which is information on the ocean surface. We have much more information about the ocean surface because we have satellites. And we have much less information about the ocean interiors because satellites don't actually look that deep inside the ocean. We do have buoys that go inside and make little measurements. We do have ship tracks that throw devices into the ocean and take measurements. But for the most part, those ocean interior measurements are very sparse, whereas we have continuous observations due to satellites. So this entire study that I'm going to be discussing is, let's say, a conceptualization of this physical motivation in an idealized setting. And the idealized setting is going to use oceananigans, which is a Julia code written to represent the ocean numerically. And so essentially, the model that I'm going to be using is going to be a 3D Navier-Stokes equation with 15 vertical levels, or basically 15 different depths, all of which constitute 256 by 256 images, if I'm going to translate this into the machine learning setting. And then you may see this extra ×3 at the end there. That's because I'm evolving the two components of velocity, so two horizontal components, as well as temperature. Another point of the data set that I'm going to describe is that it's actually non-stationary, which will be akin to climate as well. The given information is going to be the free surface height. So this is surface pressure, stated differently, and at different levels of coarse graining. And the predict information is going to be the 3D interior ocean state given that free surface height. The machine learning method was trained to produce the entire three-dimensional field simultaneously, and it was trained on all the different levels of coarse graining simultaneously. I've also tried variations of this where I only pass in one level of coarse graining of free surface height and only predict one level of interior. But in the end, I just decided to just produce everything at once since it was just conceptually easier. And plus neural networks can do that. So I just leveraged that already. All the code was written in JAX, but I also wrote it in, or used a Julia code as well to do this. And it all gave very similar results no matter how I did it. So to start off, I just want to show you kind of what the simulated fields look like, both for the free surface height, here denoted by eta, so that's the first column, as well as the east-west velocity, u, that's the second column, the north-south velocity, that's the third column, up-down velocity, that's w, and the temperature field in the last column. So everything that I'm going to be showing here is basically given this image over here, predict these 4 images over here. I'm showing a 2-dimensional slice, not the 3-dimensional field, just for simplicity of presentation. And here it's taken at a particular 400-meter depth, but the neural network is going to aim to produce things at every single possible depth of the simulation. Any questions so far, at least about the setup? And feel free to speak up or write in chat or whatever else. And I'm happy to wait a few seconds for people to gather their thoughts.
I had a question about the representation of like the interior state. Are those basically just like almost like RGB channels that are completely independent, or are they somehow like correlated or some sort of like relationship between them captured if it's like based on Navier-Stokes or something?
Yeah, so there are relationships that'll be captured between them because of Navier-Stokes equation. Like the U and V velocity are related to the W velocity through incompressibility, for example. And so the different channel outputs of the neural network, which is technically the score function, not necessarily the fields themselves. So there's a slight subtlety there, but you can overall think of it as trying to produce these things.
Sorry, to clarify the question, I guess like not in terms of ground truth, in terms of like how the diffusion model sees them. Like, is there some sort of like architecture awareness of the like underlying equation?
Yes, because I'm using convolutional layers, those account for correlations between the different RGB channels. And also because I'm using a 2D unit, it accounts for the spatial correlations between each image. So yeah, the convolutional neural nets account for both the RGB correlations, let's say, as well as the spatial correlations.
Got it. Thank you so much.
Yep, no problem. And again, anyone feel free to ask questions at any time. Okay, one question so far. Good. Don't be shy about asking questions. Okay, so just to show what the training and test set look like and to emphasize a little bit about this point on non-stationarity, here I'm showing one particular metric, which is the L1 norm of the field. So just taking the absolute value of every pixel and adding up all the pixels, but for different depths and different fields. So here I'm showing 4 different depths, 4 different fields. That gives you 16 total panels, and all of them are a function of time. And you see 3 colors within each one of those panels. One of them is blue, the other one is red, the other one is orange, corresponding to earlier times of the simulation, mid-time, and end time. The ocean simulation starts from rest, meaning I start an ocean with no ocean currents, 0 ocean currents, flat top, stratification as well, so layers of density. But then I allow the simulation to progress and wait for it to reach a statistically or a semi-statistical steady state, but not quite, because all of these lines, you see that they're not flattening out. Some of them continue onwards, downwards, like the bottom right. So the blue part is considered a transient of the simulation. It's not very physical. It's just the ocean state getting to where it wants to be based off of the simulation parameters. And that's just discarded and just thrown away as part of the data set. Then there's the red region. That's the part that I actually use for training of the neural network. And then there's the orange region, which is, I'm going to actually only be using the very end of that orange region, which corresponds to 50 years from the future of the end of the red region. So all of the inference that I'm going to show you here is from 50 years in the future of the simulation, something that the neural network is guaranteed to have never been exposed to. The ocean does decorrelate fairly slowly, but not so slowly that 50 years in the future can't be considered essentially independent of the past. So this is just the setup for the problem. Train over about 300 years and then infer 50 years later from that. Okay, so just to say that I'm not trying to do any cheating and let's say, flatter the results of the generative model. Okay, so some results. So given the free surface height, which looks like this image over here, the goal is going to be to, so this is taken from 50 years future in the simulation. So I just run the model 50 years further from anything the neural network has seen. And then its goal is to infer this zonal velocity field at a 50-meter depth, only given the sea surface height. But I'm using a generative model, so I can infer as many different fields as I want, conditioned on the information I have. And I generate 100 samples given this conditional information, the sea surface height. I'm only going to show 2 of them here, but keep in mind I actually have 98 other ones. And what I'm showing here is an AI sample conditioned on the information that was given. By eye, you see a lot of similarities between the OCS, which is, again, kind of the ground truth coming from the ocean simulation, and the generative model that was conditioned on that sea surface height. It's a similar story for the other AI sample. You see that it looks extremely similar to the velocity components of the ground truth. And I generated 100 of these, so I can also take an ensemble average, and even the ensemble average looks like the ocean simulation. So this situation that's arising here means that we're much more in the functional relationship regime between inputs and outputs than the marginal regime, but we'll jump into that later. This is just saying that the free surface height is extremely informative of the ocean interior, at least in this simulation. Now, the next thing I'll show, because by eye, it's kind of hard to tell the difference between the ocean simulation output and the generative model output. I'm just going to take the difference between the ocean simulation and the AI mean, and I'm going to put it over here. So here you start seeing that there are actually some differences. For example, the little yellow regions means that there's a high discrepancy, whereas the darker blue regions means that there's a very low discrepancy between at least the mean and the ground truth. And there's actually a nice physically plausible reason to expect there to be more, let's say, discrepancy in the top of the pixel or top of the image, as well as that little region on the left in the center of the image as well. One of them has to do with a lot of baroclinic eddies. So there's a physical mechanism for it. And at the top, there's a convection, which we expect to be more decorrelated with the surface properties, at least instantaneous surface properties. But again, I'm generating an ensemble, and I can look at the standard deviation of my ensemble. And that's what I'm plotting here on the right. And the comparison to make here is that this mean discrepancy actually looks a lot like the standard deviation from the ensemble. And what this is telling you is that the uncertainty of the generative AI model is consistent with the errors that we see when we're using the mean as a prediction for the ground truth. And this is a theme that's going to repeat itself a few times. I'll stop here and open it up for questions.
I think there's a question in the chat.
Let's see, can you repeat it for me?
Yes. It says, was the training data fed into the model in the time series order?
No, I shuffled it in time. And so every epoch, the time was shuffled over the training range.
And then I also have a question. Could you repeat again how the like ensemble is generated? And is that from like a fixed like X input of the surface information, or is it also kind of over a diversity of surface information?
Nope, just over one surface information. Yeah, because generative models, they draw from a conditional probability distribution. For one piece of information, it'll give you many different outputs. Any other questions?
Okay, thank you, Andrew. I have a tiny question. Is for your aim of this topic. So your topic is the surface to the seafloor. So what you want is how we can get from the satellite observation from ocean surface, and we know what's the ocean stratification on the interior, or you want to know for the seafloor topography, things like that. What's the aim? Sorry, a little bit complex.
So the aim would be to get the let's say, stratification and currents underneath the ocean. I take it for granted that the topography or bathymetry are known because there are other measurements that people make of what the actual bathymetry and topography of the ocean would be. And in fact, when going to more realistic data, I'd actually use that information in addition as conditional information for the model. So with more realistic data sets, I'd use sea surface salinity, sea surface temperature, sea surface height, as well as the bathymetry underneath in order to try to infer what the ocean currents are. But
Okay.
here, a simpler case, it's a flat bottom for the simulation.
Okay, so you're saying you compare the AI result with the model
Yes.
result, right? Okay, and another thing is we know the ocean has stratification, and for the upper ocean, it's more turbulent. There has wind flux, and ocean itself also has a stable, deeper part and a relatively active upper part. So there has some interface, like ocean entrainment at the middle of the ocean. So how you deal with these things, because we know the water mass are very complex in the interior ocean, and if you only see the surface, you will not know the water mass where it goes, and it has a lot. It's very meaningful for the ocean interior. So how you deal with this part?
Yeah, so here, at least when going, this is beyond what I'm presenting here, but thinking ahead about where I'd want to take this. To do the inference from surface to interior requires extra information. Here, the extra information is supplanted by ocean models. And you could imagine that in a more realistic setting, this extra information will be supplanted with both reanalysis as well as free-running ocean models to make an inference. Now, you're correct that there are certain regions of the ocean where I wouldn't expect surface information to plausibly constrain the output of the model. With generative models, this is okay. Like I'm perfectly happy with living with very large error bars saying like, hey, we don't know this. And that's something that a generative model will tell you. It's like, this is something we really don't know. Then the question for us as scientists is, okay, what kind of extra measurements do we need to make in order to reduce the uncertainty? Can we reduce the uncertainty even, or do we have to live with it? The nice part about the generative methods is that it lets us start wrangling with these uncertainties in a meaningful way, since we don't produce just a single answer for the ocean interior. We'll just produce a range of answers for these subsurface properties.
Thank you.
Any other questions?
Thank you. So I was wondering about the residuals and the L1 loss. So it seems like there's a lot of different target variables, and they are responding to different value ranges. And I feel like, so can you go back to the last slide, like where you have the L1 loss?
This is not the L1 loss. This is the L1 mean of the simulation. So this has nothing to do with the machine learning or the training. This just has to do with, I am visualizing where, like in the physical simulation, the data set is being extracted from, but I'm not visualizing the loss curve here. Although it looks a lot like a loss curve. For score-based diffusion models, it uses the denoising score loss is what I used for everything. So that's an L2 loss.
Okay. Yeah, thank you. Thank you.
And again, maybe just another clarifying question on this L1 loss. The point of this slide is just to show that there's like some degree of distribution shift between like training set and test set, and you're hoping that the model is capturing like the underlying actual surface to interior relationship, not just like memorizing the distribution, right?
Yeah, exactly. And that's also why I choose some point 50 years in the future, just to guarantee that it's not like just interpolating between data points that it's seen before, at least temporally, that it really is capturing something about the simulation distribution. Yep. I'll jump back to where we were here. Right, and the standard deviation. One more thing I should point out in this slide is that you see that the velocity components that I'm plotting here are range from 5 to -5 centimeters per second, whereas the here the scale of the standard deviation goes from 0 to 2 centimeters per second. Just to say that the errors are smaller than what they appear. I just had to make it look a little larger as compared to the original scale. So this is just for the zonal velocity at a particular depth. But I also did this for the vertical velocity, and it's a very similar, or the north-south velocity. It's a very similar story. I have more to say about the vertical velocity here. And the main comparison that I'd want to draw everyone's eyes to here is, so for this last row that I have plotted here, the vertical velocity. Firstly, just from the mean discrepancy and the AI standard deviation, you see that it's a lot larger, or there's a lot of activity in the north and in the eddying region in the west, or the left part of the panel. Again, this is because vertical velocities in the ocean are things that are carrying convective plumes, so there's just a lot more uncertainty associated with this. This also goes towards the previous question of like, what can you predict, what you can't, how do you live with not predicting something? And this is a good example of what you can't predict given the current level of information, at least to a certain level of accuracy, because the vertical velocities are much more difficult to infer. But one thing that you see from the ocean simulation and the AI mean, here looking again at the bottom row, if you look at the north part of the panel or the very top picture, you see that there's a lot more white space there than there is in the actual ocean simulation. And if you look at the two samples, you see just much more blue and red in the top of the image versus the mean. And that just goes towards showing the uncertainty in predicting whether velocities are going up or down in the domain there. So this is where information is being washed away a bit from the averaging procedure, and where things are less predictive. Again, generative models let you deal with this uncertainty where when you can't predict, you still produce something physically plausible based off of what you've seen in the past. The temperature field is a bit easier to predict. So yeah, the temperature field is well predicted by the generative model since it's evolving on a semi-slower timescale for this depth. Okay, so this is for doing the inference with the full resolution sea surface height as given by the simulation. Now I'm going to go to a different question, which is how much information can we lose about the surface and still make a good inference about the interior? And this is related to different satellite missions that we have because we just switched from essentially a VISO class missions, which are roughly on a 200-kilometer length scale for measuring the sea surface height, to the SWAT-based length scales, which are more akin to like 10-kilometer or so, depending on exactly the sampling frequency and where you are. So it was motivated by this switch in satellite missions that we've recently experienced in oceanography. So here I'm already showing a coarse-grained sea surface height because I already showed the full resolution one. And what I'll do is I'll continuously coarse-grain this more and more and more and ask the same question. How much of the ocean is constrained by the information that I'm providing, with just basically 4 pixels of information at the very bottom to, well, much more at the top. And when I look at the output of the generative model and I take my 100 samples and then average them, you already see something different happening here. You see that at the top, there's a lot more spatial structure. And as you go down and down and down in resolution for making this inference, a lot of that spatial structure is washed away. But when you look at the different samples, they're all still reasonable, plausible ocean interior states. So another thing that you can see is that the standard deviation of the ensembles are increasing as we decrease the amount of information that we're providing. This is just saying that when we provide less information, we have more uncertainty. And that's one of the benefits of generative models. You don't look for this deterministic relationship. You have a range of plausible choices, and it's consistent with the previous simulations. Any questions?
How is the generation like invariant to the dimensionality of like the conditioning information? Like how can you only pass in 4 pixels versus like a full resolution image and generate the same way?
So there's lots of ways to account for multimodal data in these generative methods. For example, if anyone's ever used DALL-E, you provide in text and it generates an image as conditional information. So you're going from very different modalities. It's not just using a convolutional neural net, or you can go from like speech to image kind of thing. In this particular case, I still treated things as a full resolution field. I just repeated the number of pixels with the same value. So for the convolutional neural net, I just did it that way.
Makes sense.
But I didn't need to do it that way. There are much more efficient ways to do the same kind of partial conditioning information. Okay, so this is a sanity check, but there's an even stronger sanity check that I can do to make sure that when you provide less information, that you reduce down to something sensible. And this is just providing essentially 1 pixel's worth of information, so only a constant value over the entire domain. And in this case, what should happen is that your data mean, the thing that you trained on, if I take this horizontal velocity field and I average temporally, that should be the same as the ensemble average over a large ensemble members. And this is one of the checks that you can do with the generative model to see that it's actually reducing back to the correct thing, that it reproduces the data distribution that it was trained on. And that's essentially what I'm showing here, that this ocean simulation mean, which is the ground truth from the time, this is over the training period, by the way. So this is what the generative model should reproduce. I'm not looking at the testing period. This is, again, a sanity check. And you see that there's more waves and wiggles in the AI mean here than the ocean simulation mean. And I think that's just because I needed more ensemble members to really reduce the variance. So that's just one statistic, which is the pixel-wise mean. There's also the pixel-wise standard deviation that you compare from the ocean simulation to the AI method. And you see that the two look very similar to one another. And it's a similar story for all the other fields too, that essentially you do reduce back to this marginal distribution, aka you forget about the free surface height and you just look at the statistics of your original data and just see that the generative model can reproduce those statistics. And it's a similar story for the other fields as well, whether I'm looking at zonal velocity, the north-south velocity, the temperature field, or the up-down velocity. They all kind of reduce in an appropriate manner to the data distribution statistics. Okay, so this is just a sanity check that the generative model does what it's supposed to. Okay, but one of the nice parts about generative models is that you also capture correlations between fields. So this is the question that was asked earlier about do these networks actually try to capture these correlations? And the answer is yes. Here I'm showing a particular statistic at several different depths. So the first row is the correlation, essentially the correlation between temperature and vertical velocity. And then I average over one of the dimensions so that things look like one-dimensional lines. And this is for the oceanographers in the audience, it's the eddy heat flux. So I subtract off the means as well. And the main point here is to see that I'm showing both the AI method shaded in light pink and the ocean simulation method shaded in blue. And in all the images that you see here, there's a lot of purple, which means that there's a lot of overlap between what the AI method predicts and what the ocean simulation outputs. And it can only be taken into account if you have correlations between different fields. They can't be produced independently from one another. Again, this is just a one sanity check. Another sanity check is that, okay, that was passing in the full resolution sea surface height. When I coarse grain my sea surface height, the coarse graining factor by 128 is essentially the full coarse graining. You see that focusing on the top row, you get very narrow red bands, which means that you have very little uncertainty in predicting this quantity. As you coarse grain more and more and more, those red bands grow larger and larger and larger, meaning that you have more uncertainty in being able to predict that quantity. And it's a similar story for the meridional heat transport, which is the heat transport going from north to south. One of the statistics that one can check on is exactly these eddy heat flux quantities. Any question over this? Here I'm taking a zonal average. So an average over the east and west coordinate over a particular depth.
Hi, Andre.
Hey.
Okay, hi, Andre. Thank you. A great talk. And I have a couple of questions, actually. So the first one is regarding the variables you are using for training the diffusion model.
Mm-hmm.
And as far as I know, winds and temperature, they have different, dynamics and different speeds, I will say, right? So did you observe any issues when training the model? Because I see from your results that the temperature is predicted very, in a correct way, whereas you have some biases for the velocities. And I was just wondering if you observe any like issues or problems during the training for these variables, maybe, winds is a bit behind the temperature. And this is my first question. And the other question is whether you can use this model to like interpolate across vertical levels of depth, like to fill some gaps or to create other, levels, depth levels. Thank you.
Mm-hmm. Yeah, so I guess I'll answer both questions. One was the predictability of fields given their different dynamics. And I didn't run into any issues in training per se. And I'd argue that these results over here, let's say, where there's a fluctuations, things aren't perfectly predicted. I think that's a physical feature rather than an unphysical one, because sometimes the level of information that you provide just isn't enough. And there is an inherent uncertainty on things. And when you have dynamics that are very fastly fluctuating or that have more eddy variability or more turbulence, let's say, like the velocity components, then you can always expect this level of uncertainty if you don't provide perfect information, as I do here. I'm not trying to reconstruct the same information like an autoencoder, right? I'm giving only one thing and trying to produce a whole range of things. So that's the statement of that part. And then the interpolation between different vertical levels, for example, or filling in the gaps, that would be a separate training procedure, which can be done, where as your input, you take in a low resolution field, and then on the output, you try to generate higher resolution fields. That's also goes under downscaling, and you can do downscaling with generative methods. And generative methods, I think, are, well, I'm kind of preaching the generative method framework for neural networks, but I really think it's the right way to do downscaling as well, or interpolation to higher resolution from coarse fields. It can do that, but not the model that I've done here, because it wasn't trained to do that. You'd have to go back to normal interpolation for what I produced here. Right, so the last thing that I'll show here, this was everything I've been showing was like at a given vertical slice. And now I'm going to talk a little bit about the ability of the generative method to reproduce vertical structure as well, because I mentioned that I was producing the entire 3D field, but I haven't shown anything yet. So this is the showing part. So to start off, the first thing I did was look at how correlated is the surface velocity to any of its subsequent lower layers. And this is what I'm plotting here in the top left. And this is just coming purely from the ocean simulation. And this is from the 50-year in the future case. So you see at the bottom, if you look at the top right dot, so the rightmost and topmost dot, that's a depth of 0. And then that 1.0 is the correlation. So you are perfectly correlated with yourself, is all that's saying. Okay, that's good. That's a good sanity check. And then for all the other depths of how the surface is correlated with the bottom, it decays in this manner. Now, I can ask the same question from the generative model, where for each ensemble member of the generative model, I can calculate this same correlation given the free surface height 50 years in the future, and produce the same statistic. Here, I'm not performing any averages, so the little bands that you see are answers produced by different ensemble members. So you get a little range of uncertainty on how well the generative model's vertical correlation structure compares to the actual simulation's vertical correlation structure. More so, I can also look at the correlation between the outputted fields. So this is a different kind of error metric, essentially, saying how correlated is the output of my generative AI model with the one ground truth that I have. And that is the AI correlation with ocean simulation colon full SSH. So in the top row, middle, this is the correlation between all the different fields of the generative AI model, so all the different ensemble members with the ground truth. Now, the far right one you see looks very similar in structure to that middle one. The difference is that in the middle one, I'm comparing to the ground truth ocean simulation. The one on the far right is purely from the generative AI method. Like I'm only essentially drawing an ensemble member from my generative AI method from the score-based diffusion model and using that as a ground truth and pretending and calculating the same statistic as I did before, pretending that one ensemble member that I drew was a ground truth. And you see that the structure between these two are roughly the same. And what that's telling you is that the ocean simulation ground truth is as plausible as an ensemble member of the distribution from the generative AI method. This is a very subtle point. Because we have a distribution that we're outputting from this generative method, that's one object that we have. But when we look in the real world, we only have one observation. So a generative model isn't going to, in a high dimensional setting, give you the perfect answer or, in one shot, just produce exactly what you observe. So the most you can ask is what I'm producing consistent with an ensemble member from my generative model? And that's what this is showing here, that the ensemble members generated by the generative model are consistent with the observations that you actually have from the ocean simulation. This is a common metric used in statistics when you try to compare distributions to observations. And it's very much related to this energy-based method. I think it's continuous ranked probability score. Except here, I'm not taking an extra expected value to produce a number. I'm actually showing the ranges of outputs here. Again, this is another statement that the AI method can actually quantify its own uncertainty a priori. A priori, just from the generative model, you can know how wrong you're going to be. So that's one of the features of a probabilistic modeling. And I also did the same exercise with coarse graining the full sea surface height. Here you see that there's a lot more uncertainties, but there are consistencies between what the AI method produces and the ground truth ocean simulation produces, except for the temperature field, which is that red line on the far right. And I think this is probably a good place to end the presentation and start opening up for questions. There's more statistics I can show that are all roughly the same theme of showing ground truth, showing the generative AI model, and having the generative model self-assess its inaccuracies and comparing that with the output from the ground truth ocean simulation. But the main takeaway that I want people to take away is that question geophysics should be reformulated as probabilistic inference questions, because oftentimes we just don't have enough information and we need to have, let's say, plausible uncertainty bounds on the kind of inferences that we're making. And the other one is that this is a good use case for generative AI. Like it does provide, at least in this context, seem to provide meaningful uncertainty estimates. And with that being said, I'm happy to open up the floor for questions.
Yeah, thanks so much, Andre. I think we have a couple minutes. Do have a couple minutes for questions? Yeah, so.
Thanks, Andre. Great talk. I'm wondering, you mentioned at the beginning that you did this in both Julia and Jax. Could you comment on why you did that and if it's like strengths and weaknesses of those two languages?
Yeah, so the reason why I did it in Jax was actually just as an excuse for me to learn Jax, as is many of these cases. There isn't too much of a difference in my mind between using a Julia and Jax for this specific question. Like using PyTorch, of course, would have been yet another option here. And for most people, I'd suggest using PyTorch just because there are already very robust libraries for doing diffusion models already built. And for Jax and Julia, that's just if you want to do more custom things later on. So the advantage of Jax and Julia, I'd say, are both of them give you extra levels of flexibility if you want to do more sophisticated things down the line. Like it's very easy, for example, in both cases to integrate neural network libraries with the neural differential equations. Whereas in PyTorch, it's a little bit clunkier. Yeah, overall, I found them both just as easy to use, and I didn't see too much of a difference. And if anyone here has used Cursor, it's probably just like a single prompt to get things to change from one to another. You know, programming languages aren't as much of a limitation as they used to be. Although it's much better trained on Python than Julia. So maybe that's a point towards Jax and Python. The training speed was about the same in both cases. Like I didn't notice anything different there. Any other questions?
If anybody on Zoom would like to ask a question, feel free to unmute and ask directly.
Hi, Andre. Thank you very much for the presentation. I wanted to ask you if you could explain again the last plots, the last correlation plots.
The bottom two panels.
Yes, the ones on the middle and on the right.
Okay, so the entire thing, right? So here, what I was doing, I was taking the ground truth ocean simulation at every single depth. So that's why and for every single field. So if you count, let's say, if we focus on the middle row and middle column, or sorry, the top row and middle column, there's going to be 60 total dots there, one for each depth, and then the 4 different fields. For each one of those dots there, or hexagons, what I'm doing is I'm comparing the ocean simulation output. So that's the ground truth. And I'm calculating the Pearson correlation coefficient with the output of the generative model for each ensemble member individually. So I have 100 ensemble members. So I calculate 100 different Pearson correlation coefficients for each depth and each field. So that's a total of, well, 60 times 100, that's 6,000 different Pearson correlation coefficients that I computed in this plot. You see that, for example, for the green curve, that one corresponds to the vertical velocity. And it's saying that the output of the generative model is, roughly speaking, at the surface even, let's say, has a correlation with the vertical velocity of about 0.8 or so. So each ensemble member is about 0.8 correlated with the ground truth ocean simulation. For the other fields, for U, V, and T, so that's the blue, orange, and brownish color, at the very top, that correlation coefficient is very close to 1. So it's just another way of showing that the images are going to be very similar to one another in terms of the output of the generative model versus the ground truth ocean simulation. Does the middle, is the calculation clear that was done for
Yes, thanks. And so the difference with the right column is, what is the difference?
The difference is that here it's a purely, I only used output from the generative model. So that's one difference. The other difference is that here, essentially what I'm doing is out of my 100 ensemble members, I'm essentially treating one of them as the ground truth. I'm pretending that this is the ground truth ocean simulation. And then I'm calculating the correlation between those 99 and that one special unique unicorn ensemble member that I chose to be my fake ground truth.
Which is not the average.
Which is not the average. It's just an arbitrary ensemble member.
Okay.
Yeah. And so you see that the two curves, the middle and the right, look similar to one another.
Okay. Okay,
Yeah.
thanks. Also, is it normal that the temperature correlation doesn't strictly decrease when the depth increases?
Yeah,
On
yeah,
the
it
left?
depends on exactly the ocean simulation here. You can even be anti-correlated sometimes. So in this particular case, it's because it's kind of a weird ocean simulation. It's very barotropic. So like for those oceanographers in the audience, about maybe 40 to 50% of the energy is in the first barotropic mode, which means that, or stated differently, that if you average all the vertical levels together, that accounts for roughly like 30 to 40% of the energy. So that's roughly seeing what you're seeing reflected here. Yeah, the non-monotonicity is I think just a weird consequence of the simulation. I have no real explanation for it. I don't expect the real ocean to behave like this,
Oh,
but maybe it does in some places.
okay. Thank you very much for the presentation and the clarification.
Yep, no problem.
Hi. Oh, sorry. I have Andre. Hi. Thank you. Great talk. I have one last question. If it's okay for you, it's a very high level question. So you explain, I think, how the generative AI model is a good fit for this probabilistic inference framework. I was just wondering if you could comment on what are other possible approaches and maybe like the specific advantages of the generative model.
Yeah, so let's see, is the question about specifically the technique I use to do the probabilistic inference, or is the question about probabilistic inference in general versus other methodologies?
No, I think, yeah, within the probabilistic inference, right? This way we can have uncertain quantification, other desirable properties. I'm just saying, do you always recommend the generative model, the generative AI framework, were there other options and, why you picked this one, I guess is my, like, I guess you can, in a way I'm saying you could use like predictive modeling, right? Or things like this. So I was just wondering if there are specific advantages that you'd like to highlight just for us to understand if we have a similar problem, should we go this route and when?
Yeah, so I'll decompose it in two parts. It always depends on exactly the question that's being asked, of course. Sometimes you have less data. Sometimes you need more inductive bias, meaning like you just need to put more theory in order to extract the information that you have. I'd say that if you have a lot of data or a sufficient amount of data, that the probabilistic inference framework is a great one to use. When you have less data, then you need to use simpler methods. For example, in this case, for inferring the components of the velocity field, in the absence of like any other information, the first step that I think most people would take would be to take the free surface height, calculate the geostrophic velocities. So that's just a function that comes from theory that people can apply. And then they can try to compare that to the ocean simulation output. I did do that, and it does capture a good portion of the simulation, but the generative method blows it out of the water for, well, inferring everything that it can. There's other theories as well, like SQG, that tries to generalize things. But, like that's in the realm when you have more theory, and they're more limited because in theory, you make more assumptions about where your data is coming from. So if you make more assumptions, then of course you can get away with simpler computations. But if you have more data, then using probabilistic inference becomes available, and also using score-based generative methods specifically is a good methodology to use. There are other methodologies like a flow matching or, well, yeah, there are other methods for drawing from probability distributions that aren't just score-based. And even within score-based methods, there are different ways of drawing samples from once you have this, what's called the score function. Overall, like because of how much technology has been developed for score-based methods, it's become a very robust framework that's used across a lot of different fields. And there's more mature software also that people could just leverage. So as an overall statement, I'd say lots of data use this. If you have less data, then maybe you want to do something more akin to like linear regression or use Gaussian processes or theory where you can take into account inductive biases a little bit more, but you add in more bias so you can get away with less data. That's always kind of a trade-off that I view in my mind. So yeah, hopefully that kind of gives some guidance. Lots of data means like, let's say 2,000 data samples or more. That's kind of like a magic number that I like to think about when it comes to generative methods.
Thank you. Yeah, that's very helpful. Thanks.
Yeah, I guess we should probably wrap it up, but thank you so much for the talk. Let's thank Andre.
Yep. Take care. Bye-bye. Great meeting everyone. Oh, and if anyone wants to ask any questions, feel free to reach out. I'm always happy to answer. Take care and have a great summer, students.